Okay, next thing is for 2.1 would be determining if multiple points are collinear. So that would tell us if they're on the same line. One way to think of it is just simply if you were to given, let's say, point P, Q, and R, and you had them plotted, and they were plotted like this. One way you could do it is simply try and draw a line through all 3 points. And you see that this one here, let's say this is Q, P, Q, and R. Simply by analyzing the graph, the plotted 3 points, you can definitely see they are not on the same line. But if you graphed it and you had P, Q, and R, and they were like this, to where it pretty much looks like they're on the same line, if I could draw a straight line. When you're dealing with something like this, the best way to find if they are collinear would be to, like we've already done, calculate the distance from, let's say, P to R, and distance from P to R would be these 2 points, and that would be your overall distance. And you're going to have to see or check, is this equal to this distance plus that distance? So the distance of PQ plus the distance of QR. And if you think about it, even if you break this line up into additional segments, each one of these segments added together should equal the overall segment. And that'll tell you if all the points are the same distance. Now, like over here, where it didn't work out, or where it was visually easy to see that they were not on the same line, if you did your overall distance here between P and R, and then you did the distance from here to P to Q, and then Q to R, because the Q is not on the line that's going between P and R, your segments, this segment to here, is going to be greater. Those 2 segments added up will be greater than the overall distance, just because Q is so far out away from this line that's going between P and R. But when they're going through the same line, like this, they're going to, no matter how many times you break the line up, it will all the segments will add together to equal the overall distance. So let's see an example of doing this. Okay, for our first example of trying to figure out if their 3 points are collinear, so if they're lying on the same line, we've got P, Q, and R. P is -2/5, Q is 0.3, and R is 8 and -5, roughly about here. And I've drawn a dotted line to see if they look like they're going to be on the same line. So now all we're going to have to do is, again, we're going to check to see your overall distance between P and R, and then you're going to add up the little segments that are broken down in it between the points, which we only have 2 segments here because we've only got 1 point in between P and R, which is Q, and that's going to break your line up into two segments. So we're going to add the distance between P and Q with the distance of Q and R, and we're going to double check it against the overall distance of P and R. So let's go ahead and do that. And I'll go ahead and give you the full distance formula again. So the distance between any 2 points, we'll just say, keep it with the P and Q like we had it before, I think. Okay, there's your general distance formula. So since we're going to do P and Q first, it kind of works out, and we're going to let P be x1, y1. We'll let Q be x2, y2. So the distance of P and Q is equal to x2, which is from Q, so it's going to be 0, minus x1, which is from P. And P has already got a negative x coordinate, so don't forget to put the x coordinate or the x value right here in parentheses. Otherwise you might mess up, might confuse you. So y2 is coming from q, which is 3. Y1 is from p, which is 5. Now we're just going to simplify. You're going to have 2 squared plus negative 2 squared. It's going to be 4 plus 4, which will be the square root of 8, which is equal to 2 root 2. Now we're going to have to do a couple more distances. So let's box that in so we don't get it mixed up with anything. Do the distance from Q to R, one of the other segments. This segment right here. And we just calculated that distance, which was 2 root 2. And this time we're going to let let Q be x1, y1, and let R be x2, y2 for our formula that we're plugging into here. So we've got x2, which is from R, 8 minus 0, this is squared, plus y2, which is from R, which is already negative, so it's negative 5 minus 3. So you're going to have 8 squared plus negative 8 squared. Sorry, this pen's kind of not really writing where I'm pointing it, so I apologize about that. 64 plus 64, and that is equal to 128. Okay. Let's see here. 128, that's going to break down to 64 and 2, so that'll be 8 root 2. Okay. So again, that's this distance here. So it's 8 root 2, 2 root 2. Okay, box that off. Now we're going to do the overall distance from P to R. And we'll let P continue to be x1, y1, and we'll let R continue to be x2, y2. So now we're going to have x2, which is coming from R, so it'll be 8 minus negative 2, negative 5 minus 5 squared. So that's going to be 10 squared, which is 100. So I'm running out of room here. I'm just going to join 2 steps together. Negative 5 minus 5, it's going to be negative 10. Negative 10 squared is 100 again. So that's equal to root 200. So you could have that as 100 times, you can break 200 down into 100 times 2. Then 100 squared, that's going to be, or the square root of 100 is 10. So this will be equal to 10 root 2. Okay, so now we just need to figure out, do these 3 points, or do the 2 different segments here and here add up to the overall length. And your overall length was 10 root 2. And is that equal to 2 root 2 plus 8 root 2? Well, it looks like it to me. So 10 root 2 equals 2 plus 8 is 10, and then the root 2's, they just tag along. This is definitely equal to each other. So they are, these 3 points, P, Q, and R, they are on the exact same line. So this dotted line can now be filled in and considered a straight line.